Hello, good evening. Welcome to another episode of Xah Talk Show. We are going to code Advent of Code 2025, Day 4, using Wolfram Language. If you don't know, I have a Wolfram Language tutorial for programmers covering everything from the ground up. So look for it, search for Xah Lee Wolfram Language for Programmers on xahlee.info. Just search it. Xah Lee Wolfram Language. HTTP no S. Okay, there, Wolfram Language tutorial. And in it, you'll find the download link on Wolfram Language, Wolfram Research website, wolfram.com. There, you can download it for free. You need to turn on JavaScript. Okay, Wolfram language is the most high-level language by a magnitude, higher level than them all, than Python, than Lisp, than Haskell, than Rust, than OCaml. Obviously, than C++ and Java. Those are kind of low level. Okay, so Wolfram language, we're gonna code that. If you are watching this offline, play at 1.5 speed or play at twice as fast. If you are here, say hi. Love to see your comments, okay? Post comments here. So we're gonna start Wolfram language. So let's start. That's my to-do. Okay, there's a bunch of my work. So let's start Wolfram language. And let's read Advent of Code. Let's see what we get. Yesterday we did day 3 part 2 and we spent 5 hours and we didn't complete it because I was going into some kind of mathematical solution. So you can see all the past Advent of Code for this year here. And so yesterday we spent 5 hours and we kind of failed at the end. We could, so maybe next week or after that, after a few months, I'll come back to it and just finish the problem. But we tried some kind of mathematical solution and didn't work out. So that was 5-hour session. So let's go to today's talk show. Okay. So today's talk show, what is warning? Okay, then something. So video check, audio check. Okay. Okay. So Advent of Code day is here. Now Advent Code is very lousy, so they have fixed layout. So you can see the layout. So for example, today is day 4. So let's open day 4, and the layout is fixed so that if you enlarge the font, let's do then part of it went off the screen. So let me do this. Let me show it in Firefox browser without JavaScript and turn off CSS. Let's see if that'll make it better. Okay, so view. Now we're gonna do my usual style, random-ish and easy. Go slow and have fun. Okay, I'm not just gonna concentrate on solving this problem. So if you are watching this offline and you are interested in solution in Wolfram language to Advent of Code, you want to skip around. Okay, just like play my video at twice as fast and skip around. Okay, so apparently now they can you see, turning off CSS, screw their website. Then you see this customized tag. Now this is illegal. Let me tell you, you see, then you look at the source code of Advent of Code. So is that part of the source code? You got this thing. You got this why is that? Let's see. So Control U to look at the source code. Actually, we are digressing here, but new page, paste their HTML, and search for Y tag. Now, why do they have a Y tag? 20. Let's search for that. you see, why do they show this this Y thing? Very interesting. Let's ignore it now. Okay, let's not. Okay, close. Okay, so event code day 5. You ride the escalator down to the printing department. They are clearly getting ready for Christmas. They have lots of large rolls of paper everywhere. Large rolls of paper. And there's even a massive printer in the corner to handle the really big print jobs. Decorating here will be easy. They can make their own decorations. What you really need is a way to get further into the North Pole base while the elevators are offline. Okay, you go down the escalators to the printing department. You need to something. Actually, maybe we can help with that, one of the elves replies when you ask for help. We are pretty sure there is a cafeteria on the other side of the back wall. If we could break through the wall, you'd be able to keep moving. It's too bad all of our forklifts are so busy moving those big rolls of paper around. Okay, some silly story. If you can optimize the work for the forklifts are doing, maybe they would have time to spare to break through the wall. Excuse me. That was me coughing. I still have cold, lingering cold virus. The rolls of paper are represented by a @ sign. The rolls of paper are arranged on a large grid. The elves even have a helpful diagram, your personal input indicating where everything is located. For example, this diagram. The forklifts can only access a roll of paper if there are fewer than 4 rolls of paper in the 8 adjacent positions. Okay, so 8 adjacent positions: left, right, top, down, northeast, northwest, southeast, southwest. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. So those are called, there's a name for this particular type of neighbor. The other type of neighbor is that you don't count the diagonals. So that's part of the cellular automata if you study cellular automata. So one of them is called, do you guys know what I mean? Comments, okay, comments. But anyway, let's skip that. So anyway, you got this grid, that's your input. So each point on the grid, each cell, you have 8 neighbors, okay? So the forklift can only assess a row of paper if there are fewer than 4 rows of paper in the 8 adjacent positions. Okay, so if it has fewer than 4 neighbors, then it can access. If you can figure out which rows of paper the forklifts can access, they'll spend less time looking and more time breaking down the wall to the cafeteria. So you got a grid, and each @ sign indicates a row of paper. Okay, so there is one of the rule is that if a cell has fewer than 4 rows of paper, then something. In this example, there are 13 rows of paper that can be accessed by a forklift marked with X, okay? So let's see. So if we look at random, okay, so let's magnify. Okay, this looks like a cellular automata problem. Okay, let's just copy the input. Okay, let's copy that. Let's do it in Emacs. Showing browser. Showing browser, then let's start code here. Wait, let's just paste that, and there is the other input. Let's copy that. Copy, switch back, and put it here, and let's say text. Okay, and let's say text. Okay, so if we view this and Shift Alt scroll, so we truly magnify it. Shift Alt. Okay, so so let's look at this is how to read. Okay, the @ sign is a problem. It would be better if you change the @ sign to something else, but let's stick with it. So this X has, okay, so fewer than 4 neighbors. Okay, one of the criteria is something about fewer than 4, right? Yeah, fuck. Okay. Fewer than 4 rows of paper. So if it has 1, if it has 0 or 1 or 2 or 3 neighbors, then there's a X. Okay, so let's check. 1 or 2 or 3 or 0. Okay, X check. This X check 1, 2. This X check 1, 2. This X check 1 and 2. This X check 1, 2, 3. Okay, this X check 1, 2. Okay, good. Now there's X here 1, 2, and 3. There's X here 1, 2. Okay, so okay, we got it. 0, 1, 2, or 3 neighbors, then it's an X. Okay, so but what is your problem? What is your problem? Consider your complete diagram of the paper row locations. How many rows of paper can be accessed by a forklift? This is like a fucking trivial. Okay, let's put it back. Let's magnify. Let's shrink, not magnify so much. Okay. Showing browser. Okay, we got that. So okay, let's get our puzzle input. So in this case, the answer is 17. So what is our personal puzzle input? Oh, big one, a big one. Copy, close. So let's go to input, paste it so we can look at. Okay, so how many lines? 139 lines. 139 odd, not 140. And how many characters per line? Let's see. 139. So it's 139 by 139 square grid. Okay, save it, close. Okay, let's work on this problem then. Copy. Let's start a Wolfram language code. Okay, and here, so select all. That's gonna be a string. Okay. So what you gonna do about this? So let's see how we solve this. So basically, you want to determine how many neighbors are there. Now, Advent of Code has this kind of problem often. So you can turn this into a matrix, but Wolfram Language has a lot of functions that deal with cellular automata. So let me show you. 3 Shift Enter to start the kernel, and let's magnify, and let's find let's say cellular automata. Do they have Shift Enter? Automatic cellular automation. So you got that cellular automation. Generate a list. Okay, let's look at the big documentation. Cellular automation. Let's turn on enlarge. Okay, let's turn on enlarge. Okay. Generates a list representing the evolution of the cellular automation. Okay, so let's see. So we got this pattern. Now we got this pattern. We want to, for each cell, so you can think of this as a matrix. For each cell, you want to look at the neighboring cells, and you want to count them. Each cell has two states, on or off. On is represented by a @ sign. Off is represented by a dot. Okay, so a dot is like 0. You can also represent it by 0. @ sign is 1, means on. Okay, so you got the matrix of zeros and 1. 1 means on, 0 means off. Okay, a matrix. Now, for each element in the matrix, you want to know how many of its neighbors are on. Okay, now since you explained in this way, it's easy to code. Given a grid, we can represent this as a matrix, as a 2D matrix. Okay, each cell is either on, represented by 1, or @ sign, or off, as 0 or dot. Okay, so then the problem is, for each cell, check all its neighbors, including diagonal. Now, what's the term for diagonal neighbors? Let's look up. Okay, so before I mentioned, so one of them is called, I forgot, but let's digress. Okay, in context of a grid, diagonal neighbors of a given cell are the cells that share exactly one corner with a given cell. Okay, there's a name for this this kind of consideration of a cell. It's called von Neumann neighborhood. Okay, so one of them is called von Neumann neighborhood, which does not include diagonals. The other one is called you see they have Stack Overflow about finding neighbors in a 2-dimensional array. Silly. So you want to look at cellular automata. Okay, let's go to Wikipedia. So because that cellular automata is a spectacular object. Okay, oh yeah, so this, if you consider the diagonal also as neighbors, that's called Moore neighborhood. Okay, that's a terminology. Now, if you only consider the horizontal or vertical, that's called von Neumann neighborhood. Okay, that was the phrase I was looking for. Anyway, so let's go back to our description. If a cell has 0 to 3 neighbors that are on, then we consider that cell as how do you put a name for that cell? Special, or the problem asks how many special cells are there. Okay, so now once we put this problem into matrix, now it's easy to do. Now it's just it's kind of now just trivial. You turn this string into a, you replace at sign by 1, the number 1. You replace the dot by 0. Then you turn it into you can turn it into a 2-dimensional matrix or nested array in Python, for example, nested list. Or alternatively, you can just deal with this as a string. Well, then okay, there are many ways. You can turn them into lines of strings. Each line is a string. Then there are many ways. Then you just loop through each character. Then you use the index to check the previous. So it's kind of tedious. Okay, Advent of Code has quite a lot of this problem. It's kind of just tedious. Okay, so what I'm gonna do now, we're gonna try to solve it. Okay, yeah. So, but I want to look for a special solution, or should I just like directly just solve the problem, use whatever means, just solve it instead of like thinking about fancy ways? So what do you guys like to see? Because how can I cure my browser hopping? What do you mean? Brave Sync is trash. Okay, stop talking about trash. Okay, Brave Sync. I don't use sync. Okay, I don't use sync feature in any browser. So, okay, stop talking about trash, guys. Now let's talk about math, or focus on the programming, or don't watch my show. So let me think about this. How we gonna do this? Yeah, we want to solve the problem. So so there are many ways. So the question is like, do I want just like focus on just how do you do this in Wolfram language? Because if I don't do that, I risk the possibility of me talking for an hour and not solving it. Because there's a lot of ways to solve this, because there is a lot, for example, so I have this dilemma. Which way? For example, array. Okay, there's like 100 functions for array. Okay, let's do it again. So it's like, okay, this still needs to be larger. I want them in 2 columns. Okay, so you see, there are like maybe 100 function on array components, array depth, array filter, array flatten, array mesh. Now, what is array mesh? Array mesh. Oh, okay. It generates. So this is what I want. This is fitting for this problem. Array mesh generates a mesh region from a array of rank D. Oh wait, no. This is a visual representation of a grid, like our problem, a grid, but it represents so-called mesh by represented by a. You see, you can rotate this. Fantastic. It turns the array into this grid. Okay, so that's what array mesh is. So that's not what we need. So array mesh, array pad, that that does the padding, which is very convenient, because otherwise, when you do this kind of problem, you have special case when you want to find the neighbors of the cells on the edge, because there's no index, you know, array out of bounds, either on top or on the side. So that in that case, you can array pad, so you automatically pad like nothing to the array, so you don't have the out of bound problem. So that's one solution. Okay, so array mesh, I mean, that's one of the useful thing. Array form, byte array format, array reshape. That is when you want to turn a, let's say, one-dimensional list to a two-dimensional array or three-dimensional array. That's what this array reshapes is. So array reduce, array resample, array reshape, array rules. That's gives the rules, specify elements in a sparse array. Okay, that shows a way to define a sparse array. Instead of, you know, a given array, it just simplified into a list of rules to create that array. Okay, so you got a center array. So that's for generate center array, creates a list of length n with elements a at the center and 0 everywhere else. Okay, it creates an array with one single element in the middle. Byte array, byte to string, center array. Center arrays, cepstrogram array. I have no idea what those are. Cepstrum array, what are those? Computes the power cepstrum of data. Okay, I don't know what that is. Computes a specified type of cepstrum of data. Now, what is that? That's some kind of mathematical cepstrum. Cepstral analysis has been used for characterization of echoes, separation of convoluted, separation of convolved signals, and pitch detection application in signal processing. Okay. Real cepstrum is computed as the inverse Fourier transform of the log magnitude Fourier transform. Okay. So computes the power cepstrum of data. So it does some kind of, you know, it's a mathematical function. It gives a number. So you have an array, then it returns a number. Okay. Wait, it returns each element into another number. Okay, that's, you know, that's for signal processing. Okay, I don't know anything about it. Complex array plot, constant array that generates array of all the same number. Coordinate bounding array box. Okay, that generates the coordinate kind of. Delimited array. So what is that? Delimited array. Oh, this is kind of a bug. It shouldn't be there. It's like delimited array document web, so it's not there. Export byte array function, compile export byte array. So why are we going through this? Because, you know, oftentimes Wolfram language has 7,000 built-in functions. Okay, so oftentimes something you want to do in other programming languages, you have to write it. Takes you an hour, and you may not be sure your solution is the best quality or robust or efficient. But Wolfram language may have it built in, so because 7,000. So oftentimes when you want to use Wolfram language to solve a problem, you want to look at what are the possible functions. So, but here, you know, I'm not too familiar with this array, all these array functions. So that's why I'm taking my time just to look at them. So that's why I'm asking you guys, should I focus on, you know, like don't look at, you know, don't talk about this, just focus, just do the problem, you know, in the basic way. Just, maybe it's tedious, but just finish it. Or I can like my usual way, I want to solve it in the most elegant, proper way. Then you need to, look at the sparse array. Okay, so these functions whose name contains array, they are basically generating arrays. Okay, structured array data represents a something something array with structure type st as specific content data. Okay, so what is that? Superseded by individual types as quantity array and symmetrized array. Okay, that's like obsolete function. Yeah, okay, so raw array. What is raw array? That's another bad thing. Why is that showing up? Net array. So, okay, so now let me think about this problem. So this problem is kind of like cellular automata. So what are helpful things? So let me just start to think about them, okay? So this, when you type this, it lists all functions with such wildcard pattern in it. So that's the best way to find the function you want. But alternatively, you click on array, then you go to the help. The help is also here. So for example, if you type array, completion, and in Xah Wolfram mode for Emacs, that's what I'm using. You can press a key, tap F to call Xah Wolfram doc lookup, and then there it is. So this page, the Wolfram documentation, there's like millions of pages. They are identical to the documentation in the Wolfram language. It come with the Wolfram language. Okay, so here is a so here's an array. So once you get to the documentation, then you go down here. There is tech notes and related guides that will help you do stuff related to this topic. Now, for example, tech notes, usually it's more technical. Okay, it's usually much more technical. So if you click on tech notes, vectors, and matrices, open it, a new tab, that is basically kind of a in-depth tutorial on everything you want to do with arrays or matrices or the what they call it, tensors, okay, which is kind of nested matrix. But this is usually very in-depth, so there's a lot to read, and they have like they have tens or hundreds of these page called tech notes. Okay, now if you go back here, so that's tech notes. Then there's tech notes on tensors. So if we click on that, so it's all about tensors and linear algebra. Okay, so go back. It's kind of in-depth tutorial. So go back, but usually then you have related guides. So constructing matrices. So you click on that, then these guides basically list all related functions. For example, when you look for array, you are probably interested in all sort of functions related to matrix or array. So there you have it, constructing matrices. So this is about, so on this particular page, it's about all functions that construct matrices. Okay, there are other functions about matrices, but this page is about constructing matrices. So you have table, array, coefficient array, sparse array, normal, band, gives value on array collection of bands for tri-diagonal. Okay, so like you can specify a diagonal of an array and it generates an array, something like that. It generates an array with those diagonal. So identity matrix, diagonal matrix, constant array, center array. So let's see, array flatten. Okay, so partition, join, pad left, pad right, array pad, Hilbert matrix, Hankel matrix, Toeplitz matrix. I don't know what these are actually. Those are matrices with particular property. Okay, for example, let's go to Hilbert matrix. gives the n by n Hilbert matrix with elements of the form. Okay, that's the definition. 1 divided by I plus j minus 1. So what does it look like? So let's check. Okay, so any matrix, so this is called Hilbert matrix. Okay, so it's generated, the definition is 1 divided by I plus j minus 1. So each entry is a fraction, and they get smaller as the row increase or the column increase. So they become smaller towards the lower right. Okay, and the denominator is j plus I minus j minus 1. So it's like just I plus j. So the column number plus the row number. So it has this form. So now what is the significance of this, I don't know, Hilbert matrix? Okay, so Wolfram language is very good if you want to learn all sort of mathematics. So I don't know what is this significance of the Hilbert matrix. We can look up Hilbert matrix. Okay, there it is, Wikipedia. So what is the why is this matrix important? There it is, very succinct definition, historical node, and so on, so on, so on. You know, and today we can ask AI. In linear algebra, a Hilbert matrix introduced by Hilbert, is a square matrix with the entries of this fraction. Okay, that is okay. So the entry also can be defined by the integral that is as a Gramian matrix. Okay, for powers of x, it arises in the least squares approximation of arbitrary functions by polynomials. Okay, so that is the significance, that it arises in the least squares approximation of arbitrary functions of polynomials. Okay, so basically you have random data. You want, like random data in 2D. Okay, so you got a bunch of dots. Each dot is two numbers, x and y coordinate. You got a bunch of dots, and they are kind of like a function. So they are not like over, but they are output of a function. You want to approximate these random dots by a function, by a polynomial function. So that's what. So this method to approximate this data by a polynomial function, that's called least squares. Okay, that's a way to find the function. Okay, so when you do this, then it says that this matrix, Hilbert matrix, comes up useful. The Hilbert matrices are canonical examples of yield condition matrices, being notoriously difficult to use in numerical computation. For example, the two-form condition number of the matrix above is 4.8 times 10 to the 5th power. The two-norm condition number, I don't know what that is. Lots of mathematics, okay? So I digressed into random things. Now I wanted to know I want to ask AI, tell me, what is the significance of Hilbert matrix? Okay, so let's ask AI. What is the significance of paste Hilbert matrix? Answer me. Okay, Gook, nice answer. The Hilbert matrix is a square matrix. Oh, it's always a square matrix. Introduced by mathematician David Hilbert in 1894 with entries defined as this. For example, that key properties, symmetric and positive definite. Obviously, all eigenvalues positive. Okay, Special case of Hankel matrix, constant along diagonals, and Cauchy matrix. Okay, so it's okay. The diagonals are, so that's constant. Oh, all the diagonals are equal. That's okay. That's obvious from the definition. All the diagonals are the same. Totally positive. Every submatrix has positive determinants. Okay, has closed form expressions for its determinant and inverse. Okay, so but what is the significance? That's my question. So primary significance, the Hilbert matrix is renowned in numerical linear algebra as the classic example of an yield condition matrix. Yield condition. So it's like a monster example. Why? I mean, I thought it's useful for something else. Its condition number in the two norm growth exponentially with size n, approximately as e to the 3.5 times n power, making it extremely sensitive to rounding errors and perturbations. Okay, I don't know what is a two norm, even though it appears well behaved, symmetric, positive, definite. This yield conditioning arises because the matrix is the Gram matrix for the monomile basis, okay, which is a poorly conditioned basis for polynomial least square approximation. Small changes in data leads to large changes in solutions when solving systems involving Hilbert matrices, okay? Historical and practical importance, originally used by Hilbert to study polynomial approximation theory and bounds on integrals of polynomials with integer efficients. A standard benchmark test matrix for evaluating numerical algorithms due to its known exact properties and extreme yield conditioning. Oh, okay. So when you have numerical methods, then you can then this matrix is helpful to test how well behaved is your numerical algorithm, something like that. Demonstrates limitations of floating point arithmetic. Okay, so that seems to be the significance. It's kind of like special, monster, kind of special example. Okay, so we are kind of far from advent of code. Okay, is this interesting? Okay, so let's go back to Hilbert matrix. Okay, so let's go back to the browser. Let's go back to Wolfram Language, list Hilbert matrix. Let's go back. So in fact, let's go here because it's so let's go to Hilbert matrix, vectors and matrices. Okay, that's a tutorial on vectors and matrices. Go back. I want to go to guides, constructing lists, constructing matrices. Okay, so there we are. So array flatten, array pad, Hilbert matrix, Hankel matrix, Toeplitz matrix, geometric matrices, rotation matrix, scaling matrix, shearing matrix, structure matrices, box matrix, cross matrix, diamond matrix, disk matrix, Gaussian matrix. Okay, let's see cross matrix. So cross matrix looks like that, obviously. Go back. Now box matrix looks like gives a square pattern of ones extending R positions from the center. So what does that mean? Box matrix R W gives a 2r plus 1 times 2r plus 1 block of ones 1 centered in a W times W matrix of 0. Okay, so you can have, let's say 10 by 10 matrix. Then you want the center to be filled with 1. So that's like a box. So it's like like this example. Okay, so that generates a matrix of this form. That's what this box matrix is. Okay, will this one be useful for our purposes? No. But okay, so now we have we got a overview of all the functions that construct matrices. Now let's see vectors and matrix. Okay, now let's try to find functions that directly give us a cell's neighbors. Okay, let's see if we can find that. In fact, we can code this quickly. Okay, so let me just start to do it. Okay, 1, 2, 3. Wait. 1, 2, 3. So 4, 5, 6, 7, 8, 9. Okay, so we got our matrix. Now I want to find, given a position of a matrix, I want it to return all its neighbors as a list. How can we do that? Okay, I know so you want to look at parts. Okay, the function parts. So let me think about this. So for example, I can parts xx and let's say 2 would be 5. Okay, it would return 5. I mean 2 sorry. Yeah, so wait. 2 is the second element and 2 is the second main element of that. Okay, so that would return 5. Okay, fuck. What did I get? What? Comma in we got, you see, Wolfram language do not like trailing commas, so you got a comma at the end of an element. Wolfram language consider that a syntax error. I mean, if you have a comma, a trailing comma, then that would be equivalent to this. Okay, Wolfram language adds a null to it, so that fuck up the matrix. So that's not what we want. So that's why it says warning. Okay, so let's remove that. So let's now remove the comma and do it. It'll be 5. Okay, see, 5. Okay, let's do it again. So you see that returns the element 5 in the middle because that's the second element of the second element. Okay, now I want it to be able to return all the neighbors. I want it to return 1, 2, 3, 4, 6, 7, 8, 9. Okay, now if I'm at 6, then I want it to return 2, 3, 5, 8, 9. How do you do that? Okay, that's the question. Let's do that. If we can do that, then it became like very trivial. Okay, we don't have to tediously do loop and check boundaries and so on. Hi, Xah Lee. Hi, Checks, Man, Firefox also censoring talk show. What are you talking about, guys? Man, Firefox also censoring your talk show. What do you mean, link? Oh, yeah, when you click the link, it says HTTPS error, right? Yeah, Firefox does that, and also Google Chrome. But actually, Google Chrome, I think I tried a few days ago, it actually works. So you just go to the URL field, Now, where's my browser? Here, go to the URL field, delete the S in HTTPS for my website, okay? Okay, so now let's actually try to solve this. Now, what we want to do is to find a function or write one so that it returns a cell, returns all the neighbors of a given cell of 2D matrix. For example, 5 returns 1, 2, 3, 4, 6, 7, 8, 9. In the above, and 6 returns 2, 3, 5, 2, 3, 5, 8, 9. Okay, so that is what we want to do. If we successfully found this function, then we consider we done with this problem for my talk show for today. Okay, so let's wander around the computing universe. Okay, so what is this? Let's use mouse. Trackball is the best. Vector and matrices. What is it talking about? So I used to read. I've been reading Wolfram Language I read. There's like over 1,000 pages manual. I read it from cover to cover. Just 3 times in different years, cover to cover. So I just read this for fun. Like what I'm doing today. You look at Hilbert matrix, you read, oh, that's what Hilbert matrix does, and then so you'll learn. So here's my recommendation. That's like off topic. So you download Wolfram Language, right? You download from my link, and then you then you just play with it, and you read their documentation. You can just read it for fun. If you are let's say college students or whatever, you are young people, so you just read it for fun. You will learn tremendous. If you read the whole thing, you would have a equivalent of a college degree, even beyond, beyond like a master's degree, if you spend 4 years just to read and understand all the functions of Wolfram language. Okay, so that's what I'm telling you guys. It's superb. It's like nothing like it. In my 30 years of computing experience, there's nothing like this Wolfram language system. Nothing, not MATLAB, not Maple, not nothing. Like competing products, there's competing products, Maple, MATLAB, Statistica, and today you have like Python with huge NumPy and so on. There's nothing compared to the Wolfram system. Okay, so let's see. So constructing matrices. Now let's see applying functions repeated. So we want to find this kind of getting the neighbors. Okay, we can do it quickly. So let me just try to do it quickly. Let's not. Okay, let me just read it. It might be mentioned. Okay, so this is the thing we are focusing on, okay? So let's focus. So you want to find the neighbors. So given a matrix, a 2D matrix, and given a particular position, a specification for the indexes, you pinpoint a particular cell in a matrix. Then you want the function to return all its neighbors, okay, including like out of bound, if there's no, the special case. So how do you do that? So one way is simply to pad the matrix. So let's quickly, okay, let's code this quickly. Now let's begin to actually matrix pad, array pad, okay. Array pad and padding on every side. Okay, array pad, okay. So yeah, array pad, yep. 2, so array pad 1. So okay, so we can do this array pad. Okay, so let's do this quickly. Array pad XX and what is the specification? You array and it pads 0. Okay, so 1. So 1 means 1 row per side. Okay, delete that, delete that, delete that. Okay, run it. Fantastic. Let's see. Fantastic and beautiful. Okay, that's what we want. Okay, so that's one method, one approach. Once we do this, then use okay. So is there a neighbor? So let's just quickly search for neighbor. Okay, NEIGH. Corner neighbors, nearest neighbors, G, neighbor data, neighbor graph, nearest neighbor graph, nearest neighbor degree. Okay, let's see. Corner neighbors is the option for various array and image processing functions that specifies whether diagonal adjacent corners should be considered neighbors. So that's an option to many functions. That's not what we want. Okay. But what functions use this option? So that would be key. So they okay, so 8 cornered components. So example. Okay, so you see this is critical, but the key, so this is an option to many functions. The key now is which function use this option. Morphological components. Jesus, what function is that? Morphological components gives an array in which each pixel of image is replaced. Gives an array in which each pixel of image is replaced by an integer index representing the connected foreground image component in which the pixel lies. Okay, that's like, so this is used in part of image processing. Morphological components. So it for each pixel it returns an integer or connected components. Okay. So you see it can, so it kind of manipulates a matrix. You see, given this matrix, it returns this matrix. Okay, but that's related to image processing. Okay. Now imagine one of advent of code question ask this, it phrase in a different way, but if you know, just one single function will solve it. Okay, that's interesting. So let's make a screenshot of this. Okay, like, because it's interesting. What? morphological components. Okay, now go back. Now what else uses, what else? Okay, not many. Chessboard distance, Manhattan distance, diamond matrix, box matrix. God. Finding the morphological perimeter of an object. Okay, so you can kind of do that. And diamond matrix, it just generates a diamond matrix. That's is that useful? No. Corner neighbors, let's go there. Corner neighbors is an option, right? Yeah, but that okay, so we need to get the parts. Now again, you need to get the neighbors. So easy way. So each, you see, normally this is how you get the part. So first of all, you got row number, then column number. So the neighbor above the row is just -1. So -1 and +1. And the column number is -1 and +1. So you can write it trivially, okay? So let's write a function. NEIGHBORS, okay, get neighbors equals to so get neighbors matrix, okay, then row column, okay, and you just return well, you first of all you pad the matrix. So block. Okay, so you block okay, so this is padded matrix equals to that. Then what you do, you just well, so before we do that, let's experiment first. So, okay, so you just say pad, actually part, and what is the matrix here? So let's just copy, okay? So part that matrix, okay? So two, so wait. Okay, so let me, okay, so you got a list. Easy. Let's just hard code it actually. Hard code it. Fuck. Oh god, this is so funny. Actually, I know what to do now. Okay, so it's like okay. We just hard code the fuck. You know, because if you got 2-dimensional matrix, you can hard code it. But if you got 3-dimensional matrix or 4-dimensional matrix, you can still hard code it. Then it becomes like, for 2-dimensional, you got eight lines of hard coded. You know, for 3-dimensional, then you got you know, you got like twice as much. Then 4-dimensional and so on. And so you can actually write a loop. But for now, let's hard code it and see what we got. So x row -1. So something like that. Okay, so -1. Yeah, so now I got a better way. Hold on a second. Now we got a better way. Anyone following me? You guys know what I'm talking about? You know, you guys don't know what I'm talking about. Let's say 3, 5. We want to get +1 -1. Okay, so let's see tuples. Okay. Okay, so wait, I got more ideas. Okay, so okay. Okay, let's run that. Fantastic. Can you see how beautiful it is? So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we don't want the one in the middle. Let's see. Plus minus. So yeah, you don't want the one in the middle. Okay, let's do it again. We are trying to get the neighbor index correct. Symbolic computation. This is the power of symbolic computation. Okay. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Fantastic and beautiful. This is the power of symbolic computation. Do you guys see what I'm doing? Okay, so actually this will you're gonna flatten it. Okay, do you guys see what I'm doing? So you got this, you got all possible neighbors. So 1, 2, 3, 4, 5, 6, 7, 8. That's the neighbors of the cell. Okay, delete that. Delete that. Okay, beautiful. Now remove our testing code. Now we don't need this we don't need to manually code this anymore. So we just we just do this. Okay, now we got this oh, you don't want them to be you want them to be, wait, 8 of them, wait, hold on a second. So 1, 2, 1, 2, 3, 4, 1, 2, 3, 4. So x is the row number, okay, plus y is the row number. So x has two variations, -1 and +1. And y has two variations, y -1 and +1. Okay, so this evaluates to, oh, okay, so y has two, so you want to flatten this, okay? Okay, then you feed that to Tuples, okay. Let's see, let me make sure. Wait, wait. Uh, 1, 2. So how do we generate this correctly? We are almost there. Anyone watching? Okay, we are almost there. So let me think, okay? Otherwise, I'll just non-stop trial and error. So you want all tuples, okay? But each tuple is so X and Y. What? 1, 2, 3, 4. Oh, but so this does not count diagonal. So wait, x plus 1 and y plus 1. Wait, that's a diagonal. So wait, 1, 2, 3, 4. Oh, so wait, so you need the zero case. So you need the zero case. Yes. Then you need to remove the zero case. You need to remove the zero case. Right. So this in this case, it returns 9 of them. I think 1, 2, 3, 4, 5, 6, 7, 8, 9. Then you need to remove the zero case. Which is, it's like annoying. So is it possible to not? I mean, you can remove it manually because that's 1, 2, 3, 4, 5. That's always the 5th element. You can drop, you can delete that element, but okay, so this is how you generate. Then you need to delete the 5th elements. Then that's inelegant. Okay, or if you do this, so yeah, you need to drop that middle. Okay, and Okay, then you yeah, let's do this. Let's copy that there. This is how we should do it. And you need to drop the so let's go to my tutorial. List. You want to go to list operations. Then you want to delete elements. Drop. Yeah, delete and items. Delete nth item. That's how you do it. So you can, yeah, you can use delete cases, or you can just actually, yeah, okay. We can, you know, what we can do is, first of all, generate it. Let me show you. Okay, then we can just delete cases that you want to delete the case of x and y. Okay, so that you see, you got this x and y. That's what you don't want that. Okay, but if you do this, it'll work. Okay, so you see that xy is gone, so you can do this. Okay, so and then okay, this generates the indexes of the neighboring cell. Okay, so let's delete that. So let's delete that. Delete. Okay, then this we don't need to manually code it. Okay, so we just basically just do this kind of. And this x would be x row, so replace x row, and the y would be x column. Okay, that returns. Oh, then it just generate that. Then you need to apply parts. Okay, then you just what you do is you map. Let me show you. Okay, so there. Okay, map function parts at wait. Let me if you don't know what splice is, it just remove the outer brackets. Okay, so let me show you. For example, ff, you have a function, you splice, it just return ffx comma y. Okay, let me show you what this wait, what? Wait, not splice. Okay, this is experimental. No, that's we are. One I want is sequence. Yeah, sequence. 1996. That's right. Not splice. We want sequence. Okay, so let me show you what that does. It just removes the square brackets. Okay. No. What you have to do is you have to do this. Yeah, well, if you want to do that, so wait. So the problem usually is you have something there. Okay, so let's say you see, so what you want is, do you guys know what I'm doing? I don't think so. Okay, what you want is which is apply. You see, what you want is this. So basically you got a function ff and you got some kind of argument, a value, a list, right? But you want to feed that to a list. So that's basically that's what you do. Okay, so that's why, that's what basically what we want to do is here. No, actually we don't need to do it. We can just say x row. Well, that is the, well, we can just say first, second. Okay, that's the part 2. Yeah, so this function, or you can say last. Okay, let's just say last, and let's just say first. They are the same thing. Okay, first x, last x. Yeah, that will return. This function will return now. This function will return the neighbors. Shall we try it? Yeah, why not? So why don't we just try it? Okay, so we need to define, so we delete that, show example of using sequence. That's what it is. Okay, it basically removes the braces. Okay, now so that's kind of example. Let's put the example somewhere at the end. That's okay. Now we back to this issue. Array padding is another example. Let's okay, so let's clean up. Okay, Wolfram language, array padding example, then create another Wolfram language block, Then let's put another example. Wait, hold on a second. Let's look at the code. So, yeah. Okay, so there, and create another Wolfram language block, and there's more things we want to move to the example. So we want to demonstrate the flatten. Okay, so we want to demonstrate this. Okay, that returns that, so you guys know. Cut, and hold on a second. So that returns that. Then we do tuples. Okay, okay, so actually we want to include the zeros. Okay, so yeah, so cut that. We want tuples, example of tuples to be that. Okay, and so wait, so cut that, paste, run it, that returns that. Okay, now delete, and tuple that returns that. Okay, that's a like good example. Okay, then rest delete. Okay, delete. Okay, so we cut, put it back, and put it there. Syntax value the whole page, showing browser. So we have now kind of cleaned up what we are doing. So it's more organized. Show example of sequence, show example of these tuples, symbolic computation, show example of this automatic expansion of, auto apply to each element of a list. And then here we show an example of the get neighbors. So now the code is like clear. What? Okay, so now let's go to work on our code. Right, that's the input. So now okay, now let me do this. Okay, so yeah, that's a tuples. Okay, that's a tuples. So we don't need, so you have to have the delete case. Okay, so we need to use the delete case. Not include. Okay, cut, put it back. Now let's do this here. Okay, now that's a better documentation. Now this is example of expanding auto apply operator to list element. Okay, so that's clear tautology purposes. Okay, now syntax correct, go to the things we are working on, showing browser, should go down. Yeah, now let's go to the things we are working on. Okay, now put it back, and a new one, Wolfram Language. Now that. So poet neighbors, yeah, so copy it. Let's run this in Wolfram Language. Paste the code. There it is. That's our matrix. That's our function. And shift enter. Wait, it's not evaluate. Oh, you forgot to give a. You have to specify which neighbor you want. Let's say 1, 2, 2, 2. 2 and 2. It should return. You see, do you know? So do you guys know? We doing Control Shift D to separate it. So Shift Enter to evaluate it, and let's say matrix form. Show that as a matrix. And this we need to turn that into a to inline documentation for this function. This is how you do it. Equals to, and this is a string. So that's inline documentation for this function. So you need to say that matrix matrix 2D column row column. Okay, that's documentation for this function. So if matrix is then cell 5 return that. Okay, something like that. That's a documentation for our matrix, and that needs to put there. Okay, so now we are doing a lot of this. So now separate these two, and when this shift enter 2 2. Okay, this is incorrect. 0 0 0 0 2 0 4 5 2 4 5 2 0 4 5 2 4 5. So it's actually returning. Oh yeah, that you forgot to add 1, because since you padded the matrix, then you need to add everything plus 1. Okay, so that's what we need to do. Plus 1. Now I need to know the default stickiness of the operator, precedence of the operator. So if you type first add x plus 1, does the x plus 1 get computed first or the first? So it turns out the first computed first, because you can click it 3 times, it will show you the connection. Okay, you see, so in other words, you do not need to put a parent. You can if you want to, but it's not necessary. Okay, so first plus x1, then the last also needs to plus 1. So now we redefine our function, and now let's test this 2. Okay, select all, go here, click, paste, shift enter. 1 2 3 4 6 7 8 9. That seems correct. Okay, that seems correct for the neighborhood of 5. Let's do it again. First of all, let's have a visual clue. Now, let's say 1 1. Okay, let's see what you get. 1 1. So you get 2 4 5. That's correct. Now, what do you say if 1 2? You should get 1 3 4 5 6. 1 3 4 5 6. Beautiful. Now, if you say 3 1 3, which is this element, the first row, the third column is 3. So the result should be 2 5 6. Shift enter. 2 5 6. Perfect. Now let's try another case. The last one, 3 3. Okay. Shift enter. 3 3 is 5 6 5 6 8. 5 6 8. Perfect. So let's make a screenshot of this. This is basically, we did it. Fantastic. Beautiful. Okay, I think we are done. So anyone watching, so what do you guys, have you guys been paying attention? Do you guys like this stream? So actually, we did it. So this function now is perfect. So can you answer the problem? Yes. So now it's trivial. Okay, 5 minutes, 5 more minutes. Okay, so given the matrix, so okay. So let's put it back. Syntax correct, show in browser. So we got this. Okay, so far so good. Yes, very good. Now all we have to do is to wait, where's our code? Oh, our code is here. Okay, now all we have to do is we need to turn this into a matrix, then apply our function to each and every cell, then just if it's not 0, we add it. I mean, if it's if more than if there are, let's see, 0 or 1 or 2 or 3 neighbors. So if the non-zero total number of them is either 0 or 1 or 2 or 3, then you consider that special. Then you just count total number of special cells. What's your opinion on Epstein files? Okay, are you guys trolling? Okay, stop trolling. I have my opinions, but today we are doing this Wolfram language. We're not gonna talk about that. So fantastic. Okay, so fantastic. Yeah, so if we're gonna code that, that'll take 10 minutes. Okay. Yeah, so if I code it without talking, it'll take 10 minutes. But if I code it and talking, doing live stream, it'll take like 20 minutes or more. But anyway, this is what we want to do, and it's fantastic. How long we've been going? We've been going almost 2 hours. Okay, let's continue. Why not? Since we are already here, okay? So, okay, so let's do it. Okay, so let's do. We have, yeah, we don't have that. We don't have. Okay, so now. Okay, now show. I want to make sure I have everything. Yes. Okay, now. Wait. Yeah. Okay, so. Yeah. Okay, so how do you turn this into a matrix? Well, Jesus, we did this before in previous advent of code, but okay, let me quickly try to code it. Okay, characters. You got character and you got characters. Represent a single character in read. There, that returns a list of characters. Okay. Okay, let me just code it. Okay. String replace sp. Okay, string replace x input. Then what do you do? Sp. Okay, so dot becomes that's not regular expression, right? No. Zero and extra rules. So you need add sign replaced by 1. Okay, do we get it right? Oh, you get string expression. Right, that's right. So okay, so you do that. Okay, then and then string split that by he's too occupied with string expression to read up on any of that. What's your opinion? No, I just read it. I just explained that. You don't know what you guys are not watching. Kind of silly. Um, so what's going on? This so what is this string expression? This oh god, I want to finish this quickly because I don't want to this is why does it return this? I don't want to end up spending like another hour and not have this done. Yeah, the people before you, they are asking about what's your opinion about this political topic, kind of idiot. So I explained that this is not the time we talk about that, okay? Today we are focusing on this Wolfram language. That's what I'm saying. Okay, I want to finish this quickly. Now this is incorrect. Now this string replace. Why does it tell me that? Oh yeah, because 0, 1. That's not a string, of course. You need to. That's you need to. That needs to be string. Idiot. So okay, so delete that. Delete that. Delete that. And go back here, 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 minute. Here, return a string. Okay, beautiful. Now that's what we want. Okay, now put the semicolon so it suppress the output. So once you have this string, then you can kind of string split at this expression. Okay, let me just code it. Okay, suppress that output. Then we are turning this into a matrix. Okay, so let me just do it. Okay, so you do that, then okay, so you do that, and okay, so you need the characters. Characters to string. Okay, so you get the list of characters, then so that's a list of characters. Basically that's it. Okay, so if you do that, that's a result. Okay, so if you guys don't know, let me show you in this Wolfram notepad. This here notepad, paste it. Okay, you run it, shift enter. So you see they become a matrix, and each of these are they are strings. You need to turn it into digit. Yeah, okay, so turn the string. So you need to map two expression to all the elements 0 and 1. Okay, so two expression map at that. Okay, basically, so copy that, go back to notebook, paste it, shift enter. So now those are numbers. Okay, if you don't believe me, Control Shift L to copy the output, and so you can see those are numbers. On the other hand, this, if you do Control Shift L, You see, those are strings, you see. So right now they are numbers because we called two expression. That /add is like map. Okay, that's a shortcut syntax for map, a function, something. So in this case, this is a function and this is a something. So we have like two maps there. So in other words, I mean, so now we can clear. So this turns it into a matrix. So let me comment. One. Okay, that line turns the matrix into a matrix. Then we just yeah. So x matrix equals to, okay, then we don't need that. Then you can say part x matrix. So now if you say, well, I mean, you don't need to do that. So copy or paste, shift enter, then you say x matrix, okay, then / matrix form. / is a postfix notation. So this is a syntactical shortcut for matrix form bracket matrix. Okay, so if you run that, it shows you that. Okay, fantastic and beautiful. And in fact, let's make a copy of these two so that because this is a good kind of a summary part of our code. Okay, well, it needs to be bigger. Okay, you don't want it to be too big because I mean because the font is super big here. Yeah, so now it's better. Fantastic and beautiful. You see this single line of expression turns this text into a matrix of zeros and ones. So you guys want to see what I'm saying? Okay, so we got a screenshot here. Where's the screenshot? Now, there. So this is today. We did this kind of thing. That. Okay. So anyway, it gets back. So now we got the matrix. Now put it back. Now showing browser, we need our previous neighboring function. So we need to copy that. Copy. So okay, yeah. So there's an error, of course, because this is not valid HTML because this greater than equal sign. That's why when you show this in browser, it automatically does a validate. Then you tell you there's a syntax error of your HTML. Now, if you do syntax color the code, so you see those greater than equal sign become ampersand encoded. Now you show in browser. Now it says valid. There's no error. So now it shows. Okay, but now we need to copy our code about this neighborhood function. So go back here. Yeah, back. Okay, then neighborhood function. Fantastic. Okay, so we don't need this test need. So now define our neighborhood function. Okay, so then so let's just quickly let's quickly solve our problem. So I'm just gonna code it. Okay, get neighbors. So this is actually inefficient, but because each time neighborhood get neighbor is called, it actually create a padded array. That's not good. So we should do the pad array to our input array instead. So but anyway, let's move on. Okay. So you want to get neighbors. Then get neighbors of a of like x and y, okay, of column, number, and row. So the matrix dimensions, okay. Okay, dimensions. In this case, it returns 1, 2, 3, 4, 5, 6, 7, 8, 9, 11. 11. Wait. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 10 by 10 matrix. Okay, 10 by 10 matrix. Then what? Then you want to 10 by 10. So 10. So array. So we want to generate a 10 by 10 array. Okay, so what? Let's say 3 by 3. We don't want to generate array, but we want to generate the index. Okay, so 10 by 10 would be, yeah, so we want the index 10, 10, and this will be a list. Okay, so it'll be 1, 1, 1, 2, 1, 3, and so on. So you see, we want the index of 10 by 10. And we don't want array, so actually now the way to do it is yeah, that's what you want. Okay, so what you got after you do that, we want all possible indexes because we're gonna map over it. Okay, so now you map over, you want to map, so let me show you. So you want to map a function. What function you want to map? You want to map this function. You have to write it. Okay, so well, and get tedious, but never mind. So let me just code it. Okay, so the function, oh god, so this would be x matrix. No, not tag name. What? Why am I get the tag name? Where does tag name came from? Not sure where that came from. So X matrix. So you want to map this function to matrix. Wait, hold on a second. So not to matrix, but to this tuple. So yeah, that will return things, but Okay, close. Okay, so yeah, 6. Did we define X matrix? Yes, X matrix there. So when you get neighbors, so let's see. Nine. Paste. Shift enter. Okay, you got a problem. 1, 1, 1. Shift enter. So what is our matrix? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So matrix 1, 1, you got, this is not correct. Why do you get 2, 4, 5? Because our X matrix, they got hard-coded something, okay? I mean, because our get neighbors, we probably hard-coded something. Yes. You see, you got the XX here. Where does that come from? This XX. Can you guys see what? You see that XX? That's a mistake. So that should be the matrix. Okay, so you need to clear that. Make sure, check one more time. Is that correct? Make sure you don't have leaked variable. Okay, I think so. Okay, paste it there, run it. Now go back here. Go back to, now go back here, shift enter. Fantastic. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. 8 neighbors, correct. Now let's say 110, the 10th item. First row, 10th column. Shift enter. It should be 111, 111, correct? Now let's say 10, 10. Okay, 10, 10. Shift enter. 1, 1, 1, 1, correct. Okay, fantastic. So our neighborhood get neighbors function now is correct. Now put it back. Now let's remember to correct the code over here as well. Okay. At XX. Okay. Shift enter. I mean syntax correct. Okay. Now let's show in browser. Back to here. Pop it out. Okay. So perfect. Now when you do this, you get all neighbors. In fact, you can paste it. Okay, you got a list of neighbors. It's all neighbors. Then you just submit. Okay, let me just show you. Okay, total. Let's see an example here. Copy. 4. Now if total hold on a second. Okay, if total is less than 4, then it's special, okay? Then 1, else 0, okay? So you want to map a function, okay, x, map that to that, okay? So do you guys see? So you can do that, okay? Then you just total it again. So I think that's it. That's a solution, okay? I'm getting impatient, so I'm not doing much examples. I mean, I'm not doing much explanations, okay? Now there's an error because function if total equals to less than 4, then x, otherwise 1, 0, so is that because I don't have a return? Not sure. Shift enter. There it is. Then just say total, okay? Total at the last output 19. So is the result 19? Does the advent of code say 19? Advent of code, let's see, go here. 13. There are 13 rows, so our answer is incorrect. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So but we get 19, so 19 is incorrect. Okay, so now we need to debug. Okay, let's see what you say. I just joined. Okay, are you parsing a text grid into binary data? Close. I'm parsing a text grid into a matrix of ones and zeros, so it's not binary data. It's just a matrix of integers. So two expression characters at string split pipeline, join it together cleanly. So solid text matrix conversion and stuff. Yes, just one. Okay. So anyway, we are very close, but something screwed up. So I think I'm gonna stop because it's pretty late. Well, so now it's 2 hours. I've been doing this for 2 hours. Why not continue? Yeah, and I want a break. Okay, so we got it wrong somewhere. I don't know where. So is it less than 4? What does the problem say? If fewer than 4 rows of paper in the 8 adjacent positions, fewer than 4. Yeah, so it's if it's less than 4. If it's 4, then it doesn't count. Okay, so so why is it not which are we using the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? Yeah, this is 10 by 10 matrix, right? This is such a simple matrix. We haven't even got to our So according to this problem, it says there are 13. Solution should be 13. Consider your complete diagram of the paper roll locations. How many rolls of paper can be accessed by a forklift? In other words, how many cells has less than 4 neighbors? I mean, less than 4 of the occupied neighbors. So less than 4 ones. So let's say 1, 1, 1, 1. Yeah, it's all represented by 1 and 0. So we got too many old results here. So we scroll down. So we got our input to expression. Yeah. And so we are turning this text into a matrix by this line of code. So we got a matrix of zeros and ones, integer. Okay, and the dot is 0, add sign is 1, that's right. And then dimension is 10, 10, okay. Then we fixed our neighboring code, which is this one, yeah. So for each neighbor, it returns this list of, for each cell in the matrix, it returns a list of its neighbors. So for example, this is the upper left cell. So the neighbors are 0, 1, 1, 2 ones, right? Okay, so suppose that's correct. Then, okay, then you just, then this would also work, you know. Then you just, so this is our matrix, check, yes. Then you just, yeah, this is a definition of matrix function. Then you just map, you just get a tuple of, tuple is all possible positions in the matrix. Okay, so you map your neighbor's function to the tuples. So you get the list of neighbors for all cells. That's what you get. Okay, then for each of these sequence of neighbors, if you total them, the result is a number, integer. That means how many neighbors that cell has. So if it's less than 4, you turn it into 1. Otherwise, you turn it into 0. Then you just map this function, this total, to all the list of neighbors, right? Then you just get that. And you total that would be, you got 19, which is incorrect from 13. Okay, I think I gotta go. Hold on a second. Hello guys, we are very close, but we didn't make it. But I have to go because I've been coding this for close to 3 hours. So actually just 2 hours and 10 minutes. we are close, but we did lots of things. So I think that's it for this. Maybe I will probably finish it offline. So let's put it back. Syntax correct, show in browser. So that's what we did. Very close. Okay, at least we got these very nice neighbor functions. Now there may be better ways to do it actually. So, but you need more time to explore Wolfram language. You see, so the whole thing is one single line. Well, actually more than one single line because you got neighbor functions, but they can, I'm pretty sure they can be made into one single line. Much better ways, but I gotta go. So yeah, so bye guys. Thank you for watching. Bye. Check. Yeah, so video check, audio check. So we're gonna go to Google.